So good afternoon, everyone. And I would first like to thank the organizers, Sourav, Saikat, and Professor Bimalendu, for giving this opportunity to attend this conference. And it has been a wonderful discussion sessions so far since last evening. And today also, when we started having the sessions, we had a bunch of fantastic talks. And today, I think I am the last speaker. So basically, between you and the tea session, I will try to hold your interest as much as possible in this talk, but let's see how it goes, okay? So we are a new group at IIT Tirupati, and we have started activities there, mostly working in two domains, one related to quantum communication, and the other related to quantum sensing and metrology. So I will briefly share a few slides on the quantum communication activities, but majorly focusing on the quantum sensing and metrology activities. That is the focus of the current talk. So with that, let me start the presentation. So I will just introduce you to our group and activities, and then finally I will shift to atomic clocks with a very brief introduction and give you a brief overview of portable atomic clocks that have been under development. And then I will talk about the next generation portable atomic clocks. In particular, I will highlight the two-photon transition based atomic clock that we are trying to currently pursue, and then address some of the challenges, opportunities, and advantages that this particular two-photon transition-based clock presents. So in our group, as you can see, we are focusing on cold-trapped atoms as well as cold-trapped ions, and a lot of activities concerning warm atomic vapor as well. So as far as fundamental basic research is concerned, we are looking at the cooling and trapping of ions, precision spectroscopy, and long-distance secure quantum communication. Some of the applications that we are interested in based on these fundamental research are single photon generation, okay, portable atomic clocks, and then network quantum memories. So we believe that there is a fundamental connection between communication, sensing, and metrology problems. And if you look at conventional communication networks, for instance, internet or the mobile telephone networks, although they are classical networks, they need timing synchronization to function efficiently. So a classical communication networks, as they become faster, higher resolution time synchronization is required, and the corresponding time stability requirements also increase. And in the near future, we hope that we would need a secure and precisely synchronized communication network for global reach. So while there has been a lot of activities in quantum communication that has been going on, we also need to boost our focus on looking into how we can precisely synchronize these communication networks for better applications. And then very recently, a group in NIST, okay, they have looked at the transmission of single photons using clock synchronization, and they have found that this actually boosts up the rate up to 6 gigahertz. So there is already a very clear evidence here that if we synchronize quantum communication networks with atomic clocks, this can reap tremendous benefits. So this is a quick overview of the experiments that we are trying to set up on quantum communication, especially looking at the interaction between network quantum memories. So you can think of this as one of a quantum node or a quantum memory, and this is another quantum memory. And we are trying to look at communication between these two dissimilar quantum memories, hoping to scale up this network at some point. So there is already a poster on this, and I think two of my students who are here, you may like to talk to them and discuss more on this issue. So please visit that poster when your time is there. Okay, so now just a quick overview of what is a clock, what constitutes a clock, and how do we realize it using atoms. So fundamentally, we need a system with periodic behavior, and it should cycle at a constant frequency. So we need to count the cycles to produce a time interval, and then agree on the origin of time to generate a time scale. So this is what the age-old norm of making something a clock is all about, right? So now, if you want to look at realizing such a clock, okay, in the atomic domain, what we need to understand is that all the atoms are fundamentally the same, and they will oscillate exactly at the same frequency, provided they're in the same environment. And so we now have a perfect oscillator, right? So one can take a bunch of atoms, okay, you can accumulate them in a trap. It can be a neutral atom trap, it can be a charged particle trap. But then what you need to do is you need to take a laser, which will be an oscillator, and then you need to drive this at resonance with the atomic transition, and you need to count the signals, count the cycles of this signal, and then derive a time reference based on this, right? So inherent in the clock instability that you can measure, you see that there is this quality factor involved, okay? And this essentially tells us that there is a distinct advantage of measuring the frequency. For instance, if you want to measure a frequency in the microwave versus frequency in the optical domain, there is a huge boost in quality factor if you do the measurement in the optical domain, right? And the clock precision, okay, goes as 1 by quality factor. So it naturally tells us that one should go to larger frequencies, which means one should shift to optical transitions if you want to make a very precise optical clock. So here is a kind of a pyramid that tells us what are the possible applications that one can look at in terms of optical clocks. And you see that at the very top of the pyramid, okay, these are clocks which are operating with state-of-the-art sensitivity at, let's say, 10-18 or 10-19 levels. And these usually serve as the primary frequency standards for any nation. And they also serve to test fundamental physics in space or on ground, okay? And then, of course, there are other variants of clocks, okay, which are somewhat portable, somewhat less resource consuming, and probably they are more well equipped to handle applications in position, navigation, timing, and synchronization. And you can see there's a whole host of activities. For instance, if you look at GPS, so how does GPS function? Basically, there's a constellation of satellites, and in each of the satellites, there is an onboard atomic clock. So basically, when somebody activates the GPS, he is essentially measuring a timing signal difference between these multiple satellites orbiting the Earth, thereby locating the position of that object or of that person precisely on the Earth. So with this application, GPS has actually evolved into a multifaceted instrument, not only for civilian purposes, but also for a lot of strategic applications. So for instance, if you look at the key strategic applications for portable atomic clocks, one of the most prominent ones would be secure communications, where you look at time sequence code acquisition, or let's say you want to improve the network timing synchronization to increase the limit on total keys shared in a QKD scheme, okay? Then you can also look at navigation and positioning, as I mentioned, with more or less than 4 satellites, and then rapid code acquisition. Also, you can look at applications for removing jammers, okay, which can trigger IEDs, okay. Finally, some of the other applications concern underwater timing applications like data logging, beacons, etc., ad hoc timing and navigation networks. So this can be very instrumental in, let's say, looking at disaster response. Okay, so for instance, whether in the case of a fire or let's say in the case of a flood, the first responders who go there, such kind of portable atomic clocks would be very useful. Then in automobile collision avoidance systems, autonomous vehicles, for instance, drones, which have a lot of applications right now, not only in, let's say, delivering goods, okay, but also in terms of looking at agriculture-based approaches using drones, or let's say in, of course, in strategic applications where you would like to use drones for surveillance or for some other purpose. Then you also need to think about these high bandwidth communications, for instance, video on demand or teleconferencing. And portable atomic clocks can also support this kind of activity. So the question then is, okay, how do these things actually work out in the real world? So many real world devices typically rely on 1 microsecond synchronization. And these are some of the current applications that are working. So for instance, if you think about mobile communication networks, or you think about power grids, or let's say you think about the stock market where a lot of rapid transactions are happening. So in those applications, this kind of a timing resolution is the current standard, and the portable atomic clocks can definitely help support these kind of applications on a much larger scale. So this 1 microsecond synchronization is typically now used via the GPS, but the issue is that the GPS signals can be intermittent, noisy, or jammed. And typically, you need a holdover clock, okay? And the holdover clock, as of now, are based either on OCXOs, okay? So these are oven-controlled oscillators, or the next generation, which is the CSACS, okay? And I will just briefly highlight what CSACS are. So typically the CSACS can be a better option because they can hold this 1 microsecond resolution for about 8 hours compared to OCXOs, which can only work for about several hours. So these portable atomic clocks, further, they are fieldable. You don't need a fancy lab to operate this, okay? And they have advantage of low size, weight, and power. So there is a considerable need to focus in this domain. So now I'll just briefly highlight within the portable atomic clocks, typically there are two kinds of applications, or let's say physical systems that one can think of. One based on the optical domain that we just discussed earlier, and then the other is the microwave. Now, if you look at the typical energy level diagram for an atom, so you have these ground states, and then you have an excited states. Typically, the excited state is about 100 terahertz away in terms of frequency scale, whereas the ground states are more or less in the separation range of a few tens of megahertz, a few tens of gigahertz, or let's say a few hundreds of megahertz. Now, the advantages, as I can show you here, is that if you look at optical clocks, okay, the local oscillator is a laser, and you can use the laser electric field to drive this transition. And so far, the market penetration for such optical clocks is almost negligible. So no commercial products as of 2022, and this is the basis for much of this R&D activity, okay? In contrast, microwave clocks has been there since the late 1950s. So there has been two variants of microwave clocks. I will just highlight their schematic architecture and show you what is the variation between the first generation microwave clock versus the second generation microwave clock. So in this case, the local oscillator is at 10 megahertz, and then its frequency multiplied up to 10 gigahertz. And so far, their market penetration is quite substantial. So the microwave clocks are the basis for all commercial atomic clocks on market today, and hopefully maybe many more future clocks as well. So this is the first generation portable atomic clock. So you have a lamp which kind of looks into this 85 RB cell, okay, and then the light is filtered, okay, and then finally that filtered light is passed through an 87 RB cell, and the signal is connected on a photodetector. Now, this 87 RV cell is within a microwave cavity, which is driving the transition, right? So you can see there's an RF excitation, and typically these were the first generation portable atomic clocks that were developed, and they are in use as of today. Okay, so then a lot of activity started on how to even scale down this device, because typically if you look up in this diagram, this microwave cavity is quite substantial, having a substantial footprint. So the question then was, how can we scale it down? So towards this end, the solution that people arrived at was the second generation portable atomic clocks, which used this coherent population trapping phenomena, okay, and they could make this device much more compact, because now you had these special diodes which are called these vertical surface MET cavity lasing diodes, VECSELs, which were very compact, and you could drive them with the current source. You could integrate the RF signal in the laser diode current itself, and you could get rid of the microwave cavity and reduce the spatial footprint as well as the power requirement. And in turn, what was seen was that these performed almost much better in comparison to the earlier microwave clocks that were being used. So here is a performance chart, okay, that you can see here. The blue one, as you can see, okay, that is the CSAC, okay. Then you have the RB rubidium thermal atomic clock. Then you have the cesium beam tube, and then all of this is calibrated against the hydrogen measure. So you have a pretty fairly good idea of how these typical thermal clocks behave. Okay, so all of them are portable, but all of them working on microwave transitions. So then the question arises: is it the end of the technology as far as developing portable atomic clocks are concerned, or can we do something better? So with that idea, the developments on the optical portable atomic clock started coming into shape. So here, for instance, there is the size of the system that you are looking at and the Allen deviation, and typically you would like to be in this regime for strategic applications. So if you look at some of the clocks that can fit in the strategic applications domain are the future optical clocks, right? And one of them is this 2-photon rubidium transition, which can fit in this domain. So what's a 2-photon transition that we're talking about? Essentially, if we look at this energy level diagram, where you have some intermediate state and some another excited state here, one photon process will be two back-to-back photons, which are going to excite the atom from the EG state to the EE state. Whereas in the case of a 2-photon transition, this is not done in a successive way, okay? Everything happens via a detuned state, okay? This is a virtual state, and the 2-photon process essentially drives the atom from the ground state to the excited state without this intermediate state in the middle, right? So what are the advantages? The natural advantage is that the first order Doppler shift vanishes at resonance. So this is one of the natural advantages that this particular system offers. Also, the energy of the 2-photon transition, okay, that the atom perceives is equal to 2h bar omega 0, which is completely independent of the velocity of the atom, okay? And what happens is that when the velocity dependent Doppler shift is cancelled, all the atoms from any velocity class may absorb at the 2-photon resonance. So there is a strong improvement in the signal without getting the additional burden of getting the Doppler broadened spectrum. So the line width of the 2-photon transition is limited only by the lifetime of the upper state. So this is one of the major reasons why this 2-photon transition seems a very attractive proposition to develop a portable optical atomic clock based on warm atomic vapor. So if you look at the signal, so you can see that the Doppler broadened line width, okay, is a faint background compared to the signal that is massively spiking up, okay, against the Doppler background. So typically in the two photon transition, the way the clock works is that you have two beams and they are used in the anti-parallel laser beam configuration. And you see that the Doppler background is almost 1/1000 of the two photon resonance in amplitude terms for these optical transitions. So this allows for a very simplified design, which is robust, compact, and extremely portable. And one of the advantages is that this transition can be directly observed through fluorescence for some of the atoms, especially rubidium.
Intensity will be similar or both the photons?
Yes, yes, that is what the idea is. So if you look at some of the technological advantage, so let's say in terms of the microwave clocks that have been developed from the first generation, second generation, compared to this optical based frequency clock, okay, so the difference automatically is in the transition, because the two photon resonance is at 778 nanometers, whereas for the microwave based clock, especially the CSAC, that is typically at around 6.8 gigahertz, and this gives frequency advantage, which leads to a improvement in the precision, okay, by an order of 10 to the 4 times, okay. The pressure shift, for instance, the cells typically have helium, so the pressure shift is also much better in compared to the microwave based cells, okay. Also, the second order Zeeman shift is having a much better lower sensitivity compared to the microwave based cells, right. So this optical transition operating at this high Q reduces the systematics, and it also gives us low phase noise, okay. So this transition is also well studied metrologically, and this can be used as a BIPM secondary representation of the second. So what is the caveat? The caveat is that the two photon transition can only be used in E1 forbidden transitions, for instance S to S or S to D or P to P, okay. So here is the typical schematic that one can use, and we are planning to develop our clock based on this kind of energy level scheme, where you see that you have the ground state 5s half. This is for the rubidium atom. So you can excite the two photon transition at 778 nanometer using this virtual intermediate level, okay, and you can spark the atom in this 5D 3/2 state, okay. And then this can decay through an infrared photon, okay, and then finally this atom also decays from this state into this 6s half state, okay. But this is kind of very weak. The majority decay happens directly using this 420 nanometer channel, and this is the signal that will be used for the two photon based clock. So this is the fluorescence at 420 nanometer that will be detected. So if you look at the typical schematic, you have this vapor cell, okay, you have a retroreflecting mirror, and then you are detecting the fluorescence in the orthogonal direction. So you are picking up the blue fluorescence on a PMT, and through servo you can put it in the laser, create a feedback system, make sure that the system is always resonant on the two photon transition, and you can have your frequency standard based on this. So there has been some initial results from the NIST group, okay, on this two photon transition, and these are kind of quite promising, which also gives us a lot of confidence that yes, definitely this is activity we should push forward. And if you look at the noise characteristics and the Allen deviation plots, so with the low noise laser, you see it is on the level of 4, 10 minus 13, and it's quite, I would say, quite promising. Hopefully, with better lasers, better intensity control, we can improve this number even further.
So, excuse me. So the counting of time will be again through optical frequencies, right?
Yes.
Here. So I guess it is going to be again more complicated than microwave clock.
No, not really, because nowadays you get combs which are very compact. So you get combs which are like, within a 19-inch rack. So you don't need this fancy combs. Like, for instance, there are multiple comb options. For instance, Menlo Systems, which is one of the well-known companies for making these combs, their systems are quite big. But let's say recently, over the past few years, Optica has been coming up with their own set of combs. Optica is another company, and their combs are actually quite compact. So if you hope that, that with the advancements in technology, we hope that the comb layout will also be more and more compact. In fact, this particular group in NIST, they are also heavily invested in developing these combs based on micro resonators, silica micro resonators. So they shine this laser beam across this toroidal shaped silica, architectures, micro architectures, and they derive a comb signal from that. So they have already shown in one of their works that you can integrate this in a very compact way.
Thank you.
So our hope is that we can look at, for the initial version that we are planning to develop, our hope is that we can target a short-term stability of 310-12 over a 1 second integration time, and a long-term stability which is less than 510-13 over a 1,000-second integration time. We hope that the entire assembly can be fit on a breadboard with a footprint of 30 centimeter by 30 centimeter, and we hope that we can deliver a prototype at the TRL4 level. Yeah.
Numbers, actually, even if you compare with the standard cesium clocks, which is just a 19-inch rack size, 3U size, or 4U size.
Right.
So they already provide 10 to the power minus 14 and like sort of 10 to the minus 15.
Correct.
So what's the point of going to 10 to the minus 13, and size wise, it will be probably bigger than that?
No. So okay. So this is the initial results that we are just highlighting, and this with the hope that we can improve. That is the hope, that there is no fundamental limitation that it has to be only at that value. So right now we are limited by the technical instrumental noise, whatever the initial results from the different groups have given us. They are mostly limited by the technical noise of their devices. So there is no fundamental limitation on why it cannot be better than whatever the results they have quoted for. And we have to be a little bit cautious here that this is only the initial target. Hopefully, as time progresses and we gain the confidence and more experience in this, we can improve these numbers.
Actually, do you have any idea like how much it can be improved? Basically, what I wanted to say that do you have any idea how these states which are involved in this rubidium atoms, they are perturbed by different things like, let's say, Stark shift or second order or first order Zeeman shift? And Vijayda is sitting here, so he has all the system. Yeah, right. Yeah, but I mean, stability also depends on different kind of systematics, because
right.
How you are going to compensate that?
Where is it?
But it will come down to 5T.
So it is coming down from here. This is pretty long-lived compared. Oh.
No, that is not long-lived. How can 5B3? It doesn't depend on that, right? It depends only on the line width of the 5D, which is.
Yeah, that's what I was expecting.
Yeah, the 5D line width is around 1.4 megahertz is mentioned.
but the detection is happening on this channel. Okay, so even if the net effect, okay, that what we are planning to do is dependent on how many atoms we can excite here, right?
Yeah, I mean they'll decay to that,
Mhm.
but why is that going to be a problem?
No, I'm not saying it's a problem. I'm saying that so far, whatever the data from these different groups who have been working here on this arena, they so far have said that their measurements, their accuracies, instabilities are so far limited by the resolution of the different instruments they're using. So there is, as such, they did not hit the fundamental limit that is posed by the lifetime of this state. That is what I'm trying to say so far.
But then you say 10 to the power minus 12 or 13 kind of stability, right?
This is the initial result that I highlighted. Yes, this one is the initial. So as you can see, this is going down.
I know, but in terms of absolute numbers, what is the so the line width is 1 point some megahertz. So how accurately are you measuring the?
No, the line width is not. No. The line width is not megahertz. That line width is on the order of 300 kilohertz.
Okay, that's okay. 300 kilohertz. That's what.
Maybe here. Did I show some?
Yeah, here. It's on this.
Here, I think I.
So are you measuring to? So your stability seems to be like a few kilohertz. You are saying.
Right.
So we'll split the 100. So you need to have a signal to noise ratio of at least 100. Okay, this. Okay, but then that is that so much better than the cesium clock? I mean.
So far, as Shubhodip said, right now it doesn't seem like we are gaining anything, but hopefully in the long run, this is going to overtake.
Okay.
Mentioned. So theoretical one can estimate, right, by substituting the value of some number of trap, maximum number of atoms you can trap, and
Right.
then lifetime of.
So there is no trap here. This is a warm atomic vapor.
That means how many number of atoms you can have in that state.
Right.
No, actually, on top of that, I think one also have to know what are the effects of, like, let's say, black body radiation or Stark shift and etc. of those two states, because those will be the fundamental limits.
That
right. But I think the black body radiation, whatever you're talking about, those things come into effect when you are, let's say, below 10 minus 15 or 10 minus 16.
No, actually, maybe that is not the case. It could come actually.
No, for instance, the cesium beam tube that you referred to, do you think the black body radiation is really limiting the?
I can answer to that. See, in cesium atom, it basically depends on the scalar polarizability.
Right.
For cesium atom, if you take ground state, so it's around 400 atomic units.
Right.
But if you go to D states, so it's 4 or 5 times higher. So that will actually continue.
Okay.
So it will give you larger,
Yeah, but that is not operating on the optical. That is operating in the microwave, right?
But the frequency shift you will have that order, right? So
Okay. Yeah, so as of now, I think there is they have not yet hit this fundamental limit that you are referring to. Hopefully, once they improve on their instruments, maybe at some point they should be hitting this natural limit that you are referring to. But that stage they have not yet reached so far.
The Doppler corrections, will that help? Yeah, because 2 photons, if it is counter propagating.
No, that is automatically taken care of. We don't need to do anything, because how the instrument is operating, the 2 beams are exactly, the key vectors are completely well aligned, right? So the first order Doppler shift is already well illuminated. Okay, and if you're talking about second order Doppler shifts, they are also they can be compensated to a large extent.
Yeah, second order Doppler. So we have done some work on cesium on this. So your second order Doppler shifts are less than 1 kilohertz.
Right.
But you will have Stark shift, which is dependent on your intensity.
Intensity, yes.
It can be several kilohertz. So
True, true.
you will also, and you in your slide you did not say helium this pressure shift.
Mhm.
What is the units? -9? Is it megahertz, kilohertz? per torr or-
Let me try and show that slide.
Yeah, here you say -9 per torr. Is it
Per torr.
hertz or megahertz or kilohertz? Because
This one I think will be probably kilohertz.
so that will be your also another problem, because you
Right.
will have to heat your cell.
Yeah, of course, of course.
And I have one suggestion for your next slide where you show this transition, how you are detecting.
Mhm.
If you detect that 420 nanometer transition,
Right.
that transition is both way transition. You can, the ground state atoms can absorb that transition and go up. So your signal to noise ratio will be lower. So you can see if there is a allowed transition from D to maybe it is allowed, right? 5D to 5P.
Mhm.
That transition, if you can somehow detect that,
Mhm.
that will be, so you don't have any atoms there. So you will get a much stronger signal.
So you mean this red one? This
No, not that one.
then
From 5D to 5P. So it will be close to the 780.
5D to 5P. You mean
Yes,
this one?
yes.
Okay, I see. Yeah, we haven't thought about this. Maybe we can think about this.
See, the other the other point is you are anyhow using a frequency comb,
Mhm.
which is the most costly part, about 3 crore.
Mhm.
And you have to also think about rest of the part, expenditure for rest of the part.
Right,
So then, and you are, let's say, gaining 10 to the power minus 15 or 16 order.
right.
Still, you are not gaining anything compared to a cesium clock that much with the price you pay.
Yeah, so
So-
far the price advantages look a little bit unreasonable, I admit. But hopefully, as time progresses, when technology improves, see, everywhere as time progresses, the cost of things usually come down. Whatever was costly 10 years ago now is more and more affordable. So now, whatever the comb, as you said, 3 crores, maybe with the improvement in technology, it will come down to a much more reasonable price.
Are there any further questions?
There are also these atomic chip clocks, right? So if you compare with them.
So you mean having an atom
nanoscale.
chip and then trapping cold atoms close to the chip? Yes, okay.
They are also portable, right? So
Yeah, but then you need a vacuum system. You need so many
that's
other
what they claim, experimental, but anyway, I don't know.
so this word portability is, I would say, it has diverse meanings in what respect you're talking about portability. Of course, if you try to compare portable, let's say the kind of system that you're talking about, with respect to that, this system is definitely much more portable because it doesn't lack this other infrastructure that is required. You just need a cell and you can have this integrated optics around the cell and you can operate this system.
May I ask a naive question? Hello? May I ask a very naive question?
Yes, please go ahead.
Yeah, so the question is, when you move from microwave domain to optical domain, of course, you have the great advantage that your quality factor goes up by
Right.
several orders of magnitude. But at the same time, if you look at the Einstein A coefficient, the spontaneous emission, that goes as omega q. So that you increase by maybe many fold. So noise is a real issue in the optical domain, whereas that's the reason, perhaps one of the reasons why people used to make these clocks in the microwave domain earlier, because it will be much noiseless. So how do you beat that noise?
Noise due to spontaneous emission, right? That's
Yes. So it goes as omega q.
Yeah, I can comment
sure,
on that.
sure.
So basically, if you look into the optical clocks are the transition are highly forbidden transition. So there is no spontaneous emission there. There is no direct spontaneous emission between the two clock states. These are not electric dipole transitions, but electric octopole or quadrupole or hyperfine induced transitions. So that has a natural line width of, let's say, millihertz or sometimes nanohertz, something on that.
They do have some lifetime. You can talk about metastable states, so they do have some
Yes,
lifetime. I would expect I think one thing I do remember that the motivation for going to microwave domain for clocks it was just this noise is much less. Okay.
No,
That was the overall. That was the overall motivation. Why people used to make clocks at microwave domain.
No, I don't think that's
I
the right
think-
thing. See,
yeah.
the motivation of the microwave domain was because at that time, no laser was available, though no laser cooling techniques were available.
Right.
And then once the lasers were available, the challenge was how to narrow down the line width of the laser.
Yeah.
So recently, I mean, if you just compare 10 years back, the typical line width of a commercial laser was a megahertz.
Right.
Nowadays, we get 50 kilohertz, and with some extra work, not some, actually lot extra work, one can get it down to 40 millihertz. That is the best reported so far.
Right.
This technology was not available in 1950s when cesium clocks was invented.
Right.
No, I'm not talking about that. When I talk about this, when lasers, after the lasers were invented, so people were thinking of going into microwave domain. One of the main reasons, if I recall, even the textbooks mentioned that thing. You look at this classical textbook, they mention that these clocks are basically made in microwave domain, because when they talk about this Einstein A coefficient, they said this is the reason why they go to lower frequencies and do it at lower frequencies, because this noise problem is almost non-existent. Okay. But then optical domain, I would expect, be it that one transition or other, I would expect that noise will be playing a much more dominant role. So how to beat the noise? That is the question.
So that's an interesting point. I think we need to think over it. At this stage, I do not have an answer to your question, but I do think that maybe not the microwave clocks gain popularity not perhaps because of the noise issue, but because they were more cost effective, and because
there are other factors also, of course.
Yeah, the technology, as Shubhadeep mentioned, the technology was not that mature at that time to develop something on the optical domain in a very portable form factor. So that is.
Even after the invention of laser, people were sticking to microwave clocks only. Okay.
Okay, let me probably in the discussion. So I think the answer to this is that right now the best clocks are actually optical clocks at 10 to the power close to 10 to the power.
Clocks, you mean? Atomic fountain?
What it says 20 minus 21. So actually the technological advances have been such that we have been able to beat this line width issue coming from the spontaneous emission by choosing suitable metastable states and using a suitable.
Okay, thank you. Thank you.